Hey there, my name is Dr. AJ Kumar, PhD, and today we are doing the 3D signed simplicial measure via the determinant. This is Abstract Algebra 12. Alright, so in 2D we had the signed area of oriented edges, which gave us, by combining them, we could get the signed area of splines, or the signed area of oriented polygons. And then in 3D, what we're going to see is a signed volume of an oriented triangle. So that's in 4D, a signed 4 measure of an oriented tetrahedron. And so we can't visualize that, but if you imagine a three-dimensional tetrahedron, a tetrahedron is just you take 4 points and you join all 4 points and then, fill in everything. If you watched my video in the information theory series on convexity, I talked about something called a convex hull, and that's maybe a way to think about this. An edge is a convex hull of 2 points. A triangle is a convex hull of 3 points. A tetrahedron is a convex hull of 4 points. It's the simplest shape you can make out of 4 points, or 3 points, or 2 points. And generally these are called simplices, and a single one is a simplex. And the convex hull of an n simplex is n points. I can't remember. Maybe it's an n minus 1 simplex because you want the number to match the dimension. I don't remember. A simplex with n points lives in n minus 1 dimensions. So a tetrahedron has 4 points, but it's a three-dimensional object. Triangle has 2 points. It's a two-dimensional, or 3 points. It's a two-dimensional object. You get the point. And this also goes down to 1 dimension, which is, if you just think of it as a single line, this is the signed length of an oriented point. That's the determinant of a 1 by 1 matrix. It gives you the signed length of an oriented point, if you want to think about it that way. And then there's these factors that you put on. So with the triangles, we had to divide by or multiply the determinant by a half to get the correct measure. In 3 dimensions, we multiply by 1/6, which is 1 over 3 factorial. In 4 dimensions, you would multiply by 1 over 24. And in n dimensions, you multiply by 1 over n factorial. And in 1 dimension, which would be on the line, you would multiply by 1 over 0 factorial, which is equal to 1. So we're going to go over an example just to try to convince you that this works. So I tried to draw an octahedron and wireframe here, and the way we're going to orient the sides is so that if you use the right-hand rule, your thumb points out of the shape. Properly, that orientation lives in 3 dimensions, or in 4 dimensions, but that's a way to come up with it, is it points out of the shape. And I just chose this. This may not be a proper octahedron. This might not be the one that's a Platonic solid. I don't really care. I chose it just because the vertices are plus or minus 1, 0, 0. That's the reason I chose it. Alright, and we're just going to first calculate its volume by hand using calculus. So first we're going to predict what we should get. So there's 8 sides, or 8 faces. The scaling factor is a 1/6, and I just chose the simplest side here, which we orient. So this point is 1, 0, 0, this is 0, 1, 0, and 0, 0, 1. We put that into a matrix, take its determinant. This is the identity matrix. Its determinant is 1. Prediction, the volume will be 8, which is the number. There's 8 of them. 8 faces times 1/6 times the signed volume of this face, of this triangular face. And that'll be 4/3. So that's our prediction naively. But we're going to actually walk through it by hand and make sure this is right. Well, not quite. I kind of got lazy toward the end of writing this. So first we're just going to use calculus to calculate the area. So we're going to take you know how with the signed area of an edge, you like formed a triangle? Well, here you would form a tetrahedron with the origin, and you're taking the volume of that little weird oblong, weird tetrahedron. That's what's going on. Okay? So the calculus approach, so here's one of those oblong, weird tetrahedrons. And there's an eightfold symmetry on each of the faces. So what we're going to do is calculate the volume just using calculus of one of these little slices. I'm sure there's a formula for the volume of a tetrahedron. I just don't know it. But we're going to calculate the volume just using calculus and then say, well, the volume of the whole thing will be 8 times whatever the volume of this little chunk is. So if you put 8 of these chunks together, you get the tetrahedron. All right, so this face on the front here, this pink face, would be given by the... It intersects the plane x plus y plus z is equal to 1. And you notice that all 3 of these vertices are on this plane, and any 3 vertices will determine a plane because they determine a triangle and then the plane that is incident with that triangle. So it intersects all 3 of these vertices, so therefore this is the correct equation. Because the way to think about it is if you have any plane that intersected these 3 points, it is this pink plane. Or it is the plane that is incident with that triangle. I cooked up the equation. All 3 of these points satisfy this equation. Therefore, this is correct. So x plus y plus z is equal to 1, or z is equal to 1 minus x minus y, or y is equal to 1 minus x minus z. That's actually the way I ended up doing it. So I for some reason, I decided to color the z's green. I don't remember why. But the way to calculate this is going to be the integral from z equals 0, that's the bottom here, to z equals 1. So this up here is z equals 1, down here is z equals 0. Of the area of this little yellow triangular slice, which depends on z, the integral of that with respect to z. Oops. So for a fixed z hat, it doesn't matter. The slice is the area under y is equal to 1 minus x minus z hat, where x ranges from 0 to 1 minus z hat. So you kind of got to stare at this picture for a while, but how do you explain this? One minus z hat, or 1 minus z, doesn't matter, is the maximum value of x such that this equation could still be true, if that makes sense. So I don't have a good reason for explaining it, but the calculation works out, and it should be 1 minus z hat. I'm also very tired, so forgive me. I know that's correct. Well, at least the calculation works out, so hopefully that's correct. Otherwise, it's a pure magic that the calculation worked. I think that this length is 1 minus z hat, and so would this one be over here. So maybe if you did 1 minus z hat minus 1 minus z hat, yeah, that probably works. And then that would give you z back, and then that would be z is equal to z. I don't know. It probably works. Anyway, so the area of this triangle would be the integral from 0 to 1 minus z of 1 minus x minus z dx, because this is the area under the, if you drew it in the xy plane. Let me switch to a yellow color. If you drew it in the xy plane, this is y is equal to 1 minus x minus z. And there's a different one of these for each z, and we're calculating this area. So this integral, I grouped the constant term, so 1 minus z minus x. And this is 1 minus z times x minus 1/2 z squared. That's the antiderivative of this, evaluated between x is equal to 0 and x is equal to 1 minus z. At x is equal to 1 minus z, it's 1 minus z squared, because this x becomes 1 minus z, minus 1/2 of this x becomes 1 minus z. So 1 minus z squared minus 1/2 of 1 minus z squared, minus, in this case, at x equals 0, both of these terms cancel out. And so we have 1 minus z squared minus 1/2 times 1 minus z squared, which is just 1/2 times 1 minus z squared. Okay, and then to get the volume, we take the integral from 0 to 1 of this area formula with respect to z. So this area so 1 minus z squared, that is, or 1/2 times 1 minus z squared, that it, oh, actually, you know what, that's an easier way to get this formula instead of calculus. If this is 1 minus z, then let me draw that. Then 1 minus z squared would be the area of, I hate this program so much. Then 1 minus z squared is the area of this square, and half of it is just the area of that triangle. That's a much simpler way. Okay, but at least it's correct. All right. Anyway, 1/2 of 1 minus z squared, and we want the integral from 0 to 1 of that. And then so I just expanded that. So you pull the 1/2 out because integration is a linear operator. Integral from 0 to 1 of 1 minus 2z plus z squared, so just FOIL that out with respect to z. This is 1/2 of, well, the integral is linear, so you can split up this sum. And I colored each of these integrals and then drew a picture, because each of these integrals are just something you should know off the top of your head if you've taken a calculus course. So this one is the area of this rectangle, which is 1. This one is 2 times the area of this triangle, which is, the area of the triangle is 1/2, and so 2 times that would be 1. And then the area under this parabola right here between 0 and 1 is 1/3. And then, so, well, this is 1/2 times 1 minus 1 plus 1/3, so that's equal to 1/6, which is just for one face. There are 8 faces, so the total volume is 8 times 1/6, which is 4/3. Which, if you go back up here, 4/3 is what we predicted, so we were right. All right, let me draw 4 pictures just to show you exactly what's going on here. And I want you to note that if you take these face orientations and port them to the edges, then the edges cancel out. So this edge right here has a, oops. So if you take this face orientation and put it here, and then this face orientation and put it here, you kind of have these edges canceling out. And so there is only, if you insist on the edges canceling out for a shape, there are only 2 possible orientations pointing inside the shape or outside the shape. And that's an important notion. And this properly belongs, again, in 4 dimensions, this idea of orientation. So anyway, I drew the XYZ plane. I drew 4 pictures, so I just rotated it. If you use the right-hand rule, so curl your fingers in the direction of, you're on the right hand in the direction of rotation. Your thumb gives the direction of that rotation. That's how you assign a direction to a rotation, is the right-hand rule, which is the same as the way we orient triangles, so, or orient splines. So to get from one of these graphs to the one to its right, you rotate it in the minus y direction, if you want to think about it that way. So point your thumb straight down with your palm facing toward the screen, and then curl the fingers on your right. Do this with your right hand, and that'll tell you the rotation that I applied to each of these graphs to get from this one. Oh my God! To get from this one to this one. And then, so you do a rotation, this rotation. That's how you get from this to this, and this to this, and etc. Okay, so in this first one, you can just look at the graph, you know the positive x, y, and z axes, and you can just read off what these points are. So this is 1, 0, 0, this is 0, 1, 0, this is 0, 0, 1. And so the matrix, there's actually 3 choices, but you have to give it a cyclical order, and all 3 of them have the same determinant. So there's a fun exercise, is that if you do a cyclic permutation of the columns in a 3 by 3 matrix, then you get the same determinant. That's fun. And since the determinant is symmetric with respect, is invariant with respect to the transpose operation, it would also work for rows. That's interesting. Anyway, so there's a couple different choices for how you can write these matrices, and I just picked them so that the one with the x coordinate would be the first entry, and that way it's really easy to compute the determinant if you know the 3 by 3 rule for determinants. Anyway, so this green triangle here, its associated matrix is the identity matrix. This purple triangle, well, you just take these columns in order. So you take the vertices, which are these points, and you just affix them. So 1, 0, 0, go to 0, 0, 1, go to 0, minus 1, 0, and there's our matrix right here. It's just taking these column vectors and smushing them next to each other. All right. This one, we're just doing the same thing. So here our points are 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. And then these two 0, 1, 0 and 0, minus 1, 0 are constant. They appear in those. I'm rotating about the y-axis, and so those ones aren't going to change. Anyway, so I think it's pretty clear what the rule is for cooking up these matrices. You take these column vectors, you take the vertices, make them into column vectors, you smush the column vectors together to create these matrices, and then there's 3 choices corresponding to the 3 cyclic orderings. Anyway, this one is 1, 0, 0, 0, 0, minus 1, and 0, 1, 0. This purple one is 1, 0, 0 down to 0, minus 1, 0 up to 0, 0, minus 1. And then over here, this orange one, we start at minus 1, 0, 0, go up to 0, 1, 0. So you see what I did? I've just, this x and z moves to x and z. Okay. And then you can reconstruct what these points are. Minus 1, 0, 0 to 0, or to 0, 1, 0, down to 0, 0, minus 1. This green matrix is minus 1, 0, 0, over to 0, 0, minus 1, down to 0, minus 1, 0. This over here, we start with minus 1, 0, 0 again, move over to 0, 0, 1, move up to 0, 1, 0, or we go 0 for the pink, purple matrix, whichever, it's minus 1, 0, 0, down to 0, minus 1, 0, over to 0, 0, 1. And what I want you to notice is that every single one of these matrices has determinant 1. So this one, the way you take the determinant of these types of matrices, It's called the expansion by minors rule. Go look that up, or go read ahead in Artin if you get Artin. But the way I've cooked these up, you just take the determinant of this little matrix down. Oops. You just take the determinant of this little matrix down here and multiply it by this thing in the top left. So the identity matrix has determinant 1. So the determinant of a diagonal matrix in particular is just the product of the diagonal entries. So this one, so 1 times the determinant of this little matrix down here. So 1 times the determinant of this is 1. Here this is 1 times determinant of this little matrix is 0 minus 1, which is 1. 1 times minus 1 times minus 1. So product of the diagonals is 1. Here it's minus 1 times, again, the determinant down here is minus 1, so total is 1. Minus 1 times the determinant of 0. Determinant of this is 1. Minus 1 times 0 minus 1. So minus 1 times minus 1. There's a lot of minus signs there, but the determinant of this is equal to 1. For the same reason, minus 1 times the determinant of this is minus 1. Minus 1, okay, here you can just take the product of the diagonals and you get minus 1. Or, correction, you get 1. And is that the last one? So each one of these matrices has determinant 1. Okay? And that's a really convenient way to... I cooked that up. So anyway, the signed volume, or the signed measure of the octahedron is 1/6 times the sum of the determinants of the colored matrices, and every single colored matrix has determinant 1. I just went over that. So it is, there's 8 of them, so, right, 1, 2, 3, 4, 5, 6, 7, 8, so 8 times 1 times a sixth, which is 4/3, which was the answer we've had the whole time, but we finally are done. So this isn't a proof in general, but I just wanted to illustrate what's going on and maybe show you how this works. And this is maybe a better way to think about the determinant. I'm going to show you a couple more features that the determinant has in more videos, but this is... Alright, anyway, thank you for listening. That's all I wanted to talk about. I hope you have a nice day. See you in the next video. Bye.